Pictures have become an integral part of life. We encounter them every day, whether on social media, television, or our own cameras. The ability of digital devices had made it easier than ever to capture and share images. However, pictures can contain more than just visual data. They can hold valuable information such as date and time, or even location in their EXIF header. Unfortunately, not every picture includes this information. When someone sends you a picture, if it's not containing the EXIF header, then you are out of luck. This is where OSINT techniques and geoguessing came in. Geoguessing is an essential skill that can help you identify the location, country, or even city of an image without the EXIF data anywhere online. And to address this challenge, we have launched the GodEye project. By leveraging AI and computer vision, we aim to assist humans in locating photos without relying on any other EXIF data.
So what are the existing technology to do this? First, we will go through the street clip model, which was created by Stanford University. We will through part. First is the training phase. This model is based on the idea of open clip model. The model flow will be like this. For every training set image, they generate a synthetic image caption by formulating the task of image localization in natural language using the following prompting template as you can see in the slide. Next, the synthetic image caption and the image will be passed through the text encoder and image encoder respectively to get their embedding. Finally, they will calculate the similarity score between the image embedding and text embedding and try to maximize the similarity score if the text and the image match with each other and try to minimize if not. So the target of this training phase is we can change the text encoder and the image encoder block so that the text encoder can encode visual information into that text. For example, when we input the text Paris, then the text encoder should encode how Paris look like in that text, and somehow it will know that Eiffel Tower is in Paris when we input the Paris text. And about the image encoder block, it can encode the information of text into that image embedding. For example, a picture captured in Paris should be encoded to represent that is Paris. And next is the inference phase, when we apply the training model in real life. In inference phase, we will input the image that we want to find the location and a list of location, like list of cities or list of countries in the world. And the output of this phase is the similarity score of each location to that image. And in this phase, they also apply something called hierarchical linear probing. So that method is start by determining the country that is most likely associated with the image. This initial identification serves as a starting point for further analysis. Street clips then proceed to narrow down its prediction, focusing on the 30 most populous cities within that particular country.
Testing, 1, 2, 3. Okay, so now I will present about the TIB Hanover model, which is used in our tool. In overview, the Earth is divided by cell regions according to S2 geometry library. Starting from the root node, which is the entire Earth, the nodes are subdivided into 4 recursively until all cells contain a maximum of a threshold Tmax images. The objective of the model is to classify the cell that correspond to the input image. So the input is an RGB image, and the output is the cell with average coordinate. To train the model, the author of TIB Hanover used a subset of Yahoo Flickr Creative Commons 100 million dataset, which contains 5 million images. Adaptive gel cell partitioning is used. Starting from the root node, which is the entire Earth, the nodes are subdivided into 4 recursively until all cells contain a maximum of T max images. The author introduced a module which is called Visual Scene Classification. To strengthen the accuracy, a deep learning model classified place category, which could be outdoor, natural, or man-made, or indoor. This is used as a complementary task to the main task, which is classifying the cells. The author also introduced a process which they call hierarchically gel classification. Cells are divided in different levels, from coarse to fine, and then classified. The final probability is calculated by multiplying the probability of each level. To predict, the above model is used to predict the cell. The coordinate is calculated by averaging the coordinates of images of that cell in the training set. For the result, the author of TIB Hanover reports the accuracy with distance from 1 km to 2,500 km on 3,000 images from the image to GPS 3K dataset. For 1 km, where a prediction is considered correct if it is at most 1 km far away from the actual location, the accuracy is about 10%. For the continental level, in which is 2,500 kilometers, the accuracy is more than 80%. We combine the two existing powerful tools in a unified, extensible framework so that the user might set up and perform image OSINT seamlessly. We create a pipeline in which there are 2 main modules: candidate generation. Since there are multiple locations on the Earth, we first need to identify the region where the image may be taken on. This module reads the input image and produces candidate locations. We utilize street clip to identify the top country candidates. The second module is the gel estimation module. This module relies on the input image and the candidates generated from the candidate generation. We utilize the latest advancement from TIB Hanover to identify the exact location of the image. After we got the coordinate given by the gel estimation module, the final module is location ranking, where we will scrape the images from Google Maps around a radius and compare with the input image and get the most similar one.
But after some experience, we know that we can improve our model by following. So here we have the future roadmap. The first feature that we're gonna implement that is the architecture detection module. By examining the architecture element in an image, such as door, windows, roof, and overall building structure, our model will make more precise location prediction. It being able to determine the location of photo based on the size of the window or the shape of the roof. The second one, module that we're gonna implement is the OCR. It stands for optical character recognition. Our model will scan any text visible in the image, identify the language, and if possible, interpret if the text indicates an address. Such detail can significantly enhance our model ability to pinpoint the location, thereby providing me more accurate result. The third one, we will implement the model which is for license plate detection and the traffic sight detection. This feature is useful when an image contains a vehicle. Each country tends to have an unique style of license plate and the traffic sign. So we will implement this for the model of more accuracy.
our friend.